In today's lecture, the main topic of discussion is the length of a curve. Intuitively speaking, given any curve, we can or we should be able to think about length of that curve. But if we analyze mathematically, it turns out that there might exist curves which don't possess length. So first, we will try to make a rigorous mathematical definition of what do we exactly mean by length of a curve. And then of course, our goal will be, given a curve, if we already know that it has got a length, then how does one calculate the length of that curve? So to start with, again we are trying to follow our intuition, and here our main tool again is Riemann integration. So let us start with a curve. Let us say it looks like this. These are the axes. Suppose this point is A and the end point is B. Now if I view this curve, I can view this curve as parametric equation. Let us say RT equals to xt yt, where t is the parameter. It ranges in between. So in a sense, I just have a function r defined on the closed interval AB such that RT is a point in R2, that is, it is a vector. So every RT has an x component and an y component. We view that as xt yt. So this is my x axis, this is my y axis. Now, how do we go about determining length of that curve? What we do is, first we take a partition of AB, let us say by 3 points, and then we plot the corresponding image of those points under R on the curve. They look something like 1 point here, 1 point here, 1 here, and the other one here. Now I join these points by a polygonal path. So this is first line, this is second line, then I get the third line and the fourth line. Now this polygonal path has got a very well defined length because these are straight lines, so I can calculate the lengths. So given any partition P, of AB, let us say the partition looks like what we do is we plot the corresponding points on the curve. So the corresponding points are RT0, RT1 up to RTN. These are points on the curve which I have drawn in the above picture. For example, this point is RT1, this point is RT3, and the last point is RT4, and so on. Whatever partition I take, I get these points and then I calculate the corresponding lengths. Now let us denote this polygon pi p. So pi p is a polygonal path corresponding to the partition P. Okay, and by mod pi p This is just a symbol. I am going to tell you what exactly is the meaning of this. It denotes the length of the polygonal path. Now, given any point xy in R2, I define by norm xy the distance of the point from the origin given by the Euclidean distance, which you know from coordinate geometry is given by square root of x square plus y square. So, given 2 points, let us say x1 y1 and x2 y2. When I talk about distance between these 2 points, that is given by norm of x1 y1 minus x2 y2 which we again know from coordinate geometry is given by x1 minus x2 square plus y1 minus y2 square. Using these formulas, now I can say that mod pi p is given by summation over k from 1 to n norm of RTK minus RTK minus 1. So, what exactly is this quantity? I will again draw the picture of the curve. It was something like this. These are the corresponding points coming out of the partition. So, the points are, let us say, RT1, RT2, RT3, RT4 and RT5, and then I have joined them by straight lines. Then the distance between RT1 and RT2 is actually given by norm of RT2 minus RT1. Similarly, if I look at the line joining 2 points RT3 and RT4, then the distance between those points is given by norm of RT3 minus RT4. And then I sum them up, that gives me the total length of the polygonal path. Now, if you believe in your intuition, it seems that the total length of the polygonal paths which I get should be less than the total length of the curve, because given any 2 points, the shortest distance between those 2 points is given by the length of the straight line which joins these 2 points. Just by that logic, then if you go between 2 points through a curved line, then the length actually you are traversing, if some such length exists, must be bigger than the straight line path. Using that, I would guess that if there is something called length of the curve, it should be bigger than this length of the polygonal path. Now, suppose I look at any refinement of the previous partition. That means I am taking more points now. So, I would take smaller distances. I would get something like this, because I am putting more points. I join them by straight lines. You see, now the length of the polygonal paths must have increased from the previous one, and it is getting closer to something which might be length of the curve. This suggests that we should perhaps look at the supremums of the mod pi p's. Now, there is a trouble in doing that. The trouble is, how do I know that some such supremum exists? That is, I am now going to look at this set, that is mod pi p, where p varies over partitions. P is a partition of the closed interval AB. I want to look at this set. This is a collection of numbers. Somehow I feel that if I can get hold of the supremum of that set, that perhaps should be called the length of the curve. The question is, why should the supremum exist? Now at this point I define something. A curve is called rectifiable if there exists a number capital M, certainly bigger than or equals to 0, such that mod pi p is less or equals to M for all partitions P of AB. Okay. The idea is that if I can get a rectifiable curve, perhaps I can go for defining the length of that curve. Well, if no such number M exists, those curves are bad curves, they are called non-rectifiable. So I will just say otherwise the curve is called non-rectifiable. Now, to make things precise, I would start with a curve R, Rt equals to xt yt. I will put some condition on x and y. These are the good curves I would like to deal with because I don't want to face some weird curves. Assume that x and y both are continuous functions of t. So whenever we talk about curves, we mean these continuous curves. That is, the x component and y component both are continuous functions. Actually, it would mean that the function r from R2 itself is a continuous function, but I don't want to go into that because right now we don't know what exactly we mean by continuity of a function which is defined on R and but its values are not in R on R2, that is a function of several variables. Okay, so let's not talk about that here right now. Let's just assume that the component functions are continuous. Okay. Now, if a curve is rectifiable, I will make another definition. If a curve is rectifiable, then the length of the curve, which I will denote by lambda AB because its parameter space is AB, as supremum over P, that is, it's the supremum over all the partitions of the interval of the quantity mod pi P. Notice that if the curve is rectifiable, this would imply that capital lambda AB, which is the length, we are going to define it to be the length, is certainly less or equals to capital M, because M is an upper bound and lambda AB is the least of the upper bounds. So it must be less than or equals to the supremum. Now, what we need is a criteria by which we can determine when the curve is rectifiable. So let's make it very clear that I am going to concentrate only on rectifiable curves, because non-rectifiable curves do exist, and rectifiable curves just mean that it has got well-defined length. And how does one define the length? Well, you look at any partition P of AB, form the term mod pi P, then go on varying the partitions, you get a set of real numbers, you look at the supremum of that set. That is called the length of the curve. Well, this is a very abstract kind of definition. Most of the time when you need to do the calculations for a specific curve, this definition will not going to work. So we have to find some closed analytic formula for finding length of a curve if the length exists. That is what we are going to do now. But the first thing is, under what conditions can we say a curve is rectifiable? Okay. So given a curve RT, so x and t both are continuous functions, I define something called r prime t, which is given by x prime t, y prime t, if it exists. That is, I am imposing more conditions on the component functions xt and yt. Okay, I am demanding that they are differentiable. Earlier I have started just with continuous curves, but it is something more. I am assuming that the different derivatives also exist of the component functions. Well, now what I am going to put is another condition. So this is my first assumption. Second assumption is x prime t, y prime t both are continuous functions. Okay, so I have taken a curve R such that r prime t equals to x prime t, y prime t. This exists. And second condition is x prime t, y prime t both are continuous functions of t where a lesser equals to t lesser equals to b. So these are the two conditions. So it is just a curve such that its component functions are differentiable and they are continuous also on the space of parameter. Let's assume these two conditions. Under these conditions, I am going to show that the curve is rectifiable. Now for that, I have to build some machinery. It's as follows. Let's suppose I have a function f from a closed interval AB to R2. Okay, then f of t can be written as f1t, f2t, that is the x component and the y component. Now assume that f1, f2 both are continuous functions. Okay, and then I am going to define something called integral a to b ft dt. This requires a definition because note that f is no longer a real valued function. It's a function whose values are on R2, so it's a vector valued function, and I'm going to talk about its integral. Now your natural intuition suggests that this integral should define vectors only. Since f is vector valued, the integral of f should be a vector. Well, that vector we define by, so this is my definition, as this vector, integral a to b f1t dt that is the x component, second one is integral a to b f2t dt. Okay. Now once I do this, then I can talk about an analog of something which we have done already. That what I do is I look at the norm of this vector integral a to b ft dt. Notice that integral a to b ft dt is a vector by my previous definition of integral. Thus, it has got a norm, that is distance from 0. At the same time, I can also talk about integral of a to b norm ft dt, because ft is a vector, so this has got a norm, and that norm now defines a function. Well, if you assume that f1 and f2 both are continuous functions, then it can actually be proved that the function norm ft, which is the integrand of the right hand integral, is actually a continuous function of t. And hence, both the integrals actually exist, no problem with that. With the assumption of continuity on f1 and f2, one can prove that both the integrals exist. Now question is, what is the connection between these two real numbers? The left hand side is norm of a vector, so it's a real number. The right hand side is the integral of now a real valued function. T going to norm ft is a continuous real valued function on the closed interval ab. So I integrate it, I get a real number. What is the connection between these two real numbers? Well, the connection turns out to be less or equals to. And you know whose analog is this? It is the analog of the fact mod integral a to b ft dt is less or equals to integral a to b mod ft dt. So it is the analog of this well-known result which we have done earlier. Okay. Now the question is, how do we go about proving it? Well, what I do is I define a vector c by this left hand formula, that is integral a to b ft dt. This is a vector. Okay. If c equals to 0, let me give a name to this inequality, call it star. If c equals to 0, then star is true. Be careful about the meaning of c equals to 0. It is not the number 0, it is the 0 vector, that is, it actually is the origin 0 0. If c equals to 0, then what happens is left hand side of star is 0, right, because length of the origin from itself is anyway 0. Now if you look at the right hand side integral, that anyway is non-negative, because the function is given function norm ft, that is also a non-negative function. Hence the inequality follows. So the genuine thing is to prove when c is not equal to 0. So it's a non-zero point in R2. Well, then I start with norm c square. You know from your usual knowledge of vectors that this is actually the dot product of c with itself. I am talking about the vector dot product in 2 dimension. This now I can write as c dot integral a to b ft dt by my definition of c. This now I can write as integral a to b c dot ft dt. This you can check yourself very easily just by writing down the definitions of integrals, writing f as f1 f2 and c as c1 c2. Now this quantity anyway is less or equals to, since this is a real number, c dot ft is a real number, don't forget that, because it's dot product of 2 vectors, it gives you a scalar. Since t is a function, t is real number, ft is a vector, c is a vector, so the dot product is a scalar. So this is less or equals to modulus of c dot ft dt. Now this is anyway lesser or equals to integral a to b norm c times norm ft, which is an elementary inequality about vectors. I will write it separately. What do I mean by this? I mean, if you have two vectors a and b, you look at their dot product, okay, then this is a number, then the modulus of this dot product is less or equals to norm of a times norm of b. This is called Cauchy-Schwarz inequality. It is not very hard to prove. You can look at any book which talks about vectors. This result will be proved there, or you can try to prove it yourself. Anyway, that would then mean that this is equals to norm C times integral a to b norm ft dt. Since I know that C is non-zero, that means norm C is strictly positive. C not equal to 0 implies norm of C is positive, it is bigger than 0. That means I can cancel this norm C from both sides of the inequality because it is a positive number. If I do that, that implies from the above inequality that norm C is less or equals to integral a to b norm ft dt. Now, using this inequality, I will go to my next result. So, I call it as a theorem. If RT equals to xt yt is a curve such that x prime and y prime are continuous functions, then the curve is rectifiable and mod pi p is less or equals to integral a to b norm of r prime t dt, where r prime t equals to x prime t y prime t. Okay. Well, this means then that mod pi p is the set of mod pi p's if p varies over the set of partitions of AB, that is a bounded set, and one upper bound at least we know, that is integral a to b norm r prime t dt, which certainly shows that the curve is rectifiable. That means to prove this theorem, the only thing I need to prove is to prove this inequality. Well, that is very easy. So, I start with the proof of this. Start with any partition P. So, let P equals to this be a partition and then I form mod pi P, that is summation I from 1 to n norm RT I minus RT I minus 1. Okay. Now, this is the quantity which I have to play around with. Well, I write that as now summation I from 1 to n norm of xti minus xti minus 1, comma yti minus yti minus 1. Okay. So these are the quantities I get, and now I can calculate the norm, which I will write as summation I from 1 to n xti minus xti minus 1. I am just writing down the expression of the norm plus yti minus yti minus 1 whole to the power half. This is the expression of the norm. Now at this point I am going to use the fact that x and y are differentiable and the derivatives are continuous, because now I need the second fundamental theorem of calculus. So this I will write as summation I from 1 to n integral ti minus 1 to ti x prime t dt square plus integral ti minus 1 to ti y prime t dt square whole to the power half. Okay. This is by second fundamental theorem of calculus. Now what does this mean? If I view this x prime t, y prime t, t going to x prime t, y prime t as a vector valued function, whatever is written here is norm of integral of r prime t. So this I can write as summation I from 1 to n norm of integral ti minus 1 to ti r prime t dt. Now I can use the previous inequality, which would suggest that this is less or equals to, by the inequality star, this is what I get. This is by star. Okay. Now by the elementary formula of integrals, that this sums up then to integral a to b norm r prime t dt, which is precisely what I wanted to prove, that the right hand side becomes independent of the partition p. Whatever p you take, mod pi t p is less or equals to this integral. This implies that the curve is rectifiable. Thus, what we have proved so far is that if xt and yt are differentiable functions and are continuous, then the curve certainly is rectifiable. Now, under these assumptions, I will try to find an analytic formula for the length of the curve. Now, let RT be a rectifiable curve. In that case, I can define, if of course the parameter varies on the set A and B, lambda AB is the length of the curve that we could define since the curve is rectifiable. The following thing can be proved, not very easy, but it's a provable fact, and which we will need is the additivity of the length. That is, if C lies between A and B, then I can talk about lengths lambda AB, I can talk about lambda AC and lambda CB. That is, when the parameter ranges from A to B, the length of the curve is lambda AB. When the parameter ranges from A to C, then the length of the curve is lambda AC. And if the length of the curve is, parameter is varying from C to B, length of the curve is lambda CB. Well, the relation is that this is equal to this plus this. That means on a curve, if I go up to this point, whatever is the length, and then I go up to this point, whatever is the length, then the total sum actually adds up to the total length of the curve, which is believable, and it can be proved, not very trivial, but if you use the definition of lambda AB using supremums and using the property of the supremum, one can prove that this is true. This is called the additivity of the length. So this relation is called additivity of length. Okay. The next is the arc length function. How does one define arc length function? It is just, I call this function S. It is a function from AB to R defined as follows. S of t equals to lambda AT if t is bigger than A. This is equal to 0 if t is equal to A. Okay. So what we are doing is that if the curve is this, let us say A and B, then from here I start moving. Suppose this is the point T, then the length which I have traversed, that is lambda AT, that is called ST. So as T varying, the way I move on the curve, whatever length I traversed along the curve is called ST. Now this function, using the additivity property of length, I will write it as a theorem, I get some property of this function that S is an increasing function. It follows very easily using the additivity of the length, which we have assumed. So proof I will not give, proof is trivial, proof is easy using additivity of length. Now there are some more important properties of this function S we are interested in, and that is given in the following theorem. So the theorem is this. Let RT be a curve such that R prime T is continuous then S prime T exists, that is a function S which we have defined turning out to be a differentiable function for each T in the open interval AB, and S prime T is equals to norm R prime T. not only differentiable, I can explicitly calculate the derivative also in terms of r prime. Remember, r prime t means x prime t comma y prime t. That is the derivatives of the component function. That new vector valued function is called r prime t. Okay, so let's try to prove this result. What I do is, first I define f of t equals to integral a to t norm r prime t dt. Notice that this function f is well defined because r prime by my assumption is a continuous function. If I take the norm of that as a function of t, it is still continuous, hence remain integrable, so the function ft would make sense. Well, I will make a slight change because what I mean here is r prime u du, because t is the limit. Well, then by the fundamental theorem, we have f prime t equals to norm of r prime t. This is by the first fundamental theorem of calculus. Okay. Now we start looking at the difference quotient. The following difference quotient I am interested in. So for h bigger than 0, I look at norm of rt plus h minus rt divided by h. Okay. Then this is certainly less or equals to 1 by h lambda t plus h, because norm rt plus h minus rt just is the length of a line, which is certainly less or equals to the curved length on the curve, which is lambda t plus h. Okay. Now this is 1 by h times, I can write as st plus h minus st by my definition of the arc length function. Okay. Now I have already proved that this lambda t plus h is less or equals to this 1 by h is just a factor, integral t to t plus h norm r prime u du. Remember, this was the result which I proved while showing a curve is rectifiable if r prime is continuous. Remember that? I have proved that lambda ab is less or equals to integral a to b norm r prime t dt. Instead of a and b, for t and t plus h I am using the same result to get the inequality on the right hand side. Okay, fine. Now this is again by my definition 1 by h f t plus h minus ft. This comes just from the definition of little f. If I go back the definition of little f, it is given here. From here it implies that ft plus h minus ft is equals to integral t to t plus h norm r prime u du. This is precisely what I have applied. Now what I want to do is take limit. Well, another observation is, which you can prove easily, that the same inequalities are true if h is less than 0. Okay, that can be very easily shown. It's not very difficult, just by the same reasoning. Now I want to take limit h going to 0 on the left hand side and the right hand side. Now the left hand side goes to norm r prime t as h goes to 0, and I look at the right hand side, that goes to f prime t as h goes to 0. But my first observation after defining f, from that it follows that f prime t is also equals to norm r prime t. Okay, that means as h goes to 0, the left hand side and the right hand side both converges to the same quantity, which is norm of r prime t. That implies then I look at what is the middle quantity, that is this one. This is the middle quantity. So this implies s prime t equals to limit h going to 0 s t plus h minus s t divided by h, which is norm r prime t, because that is the middle quantity. And this is precisely what I wanted to prove. Now this has got some interesting consequences, which is precisely what we want to look into. That if I look at now lambda AB, what is lambda AB? That according to my notation is SB minus SA. But this then by the second fundamental theorem is integral a to b s prime t dt. This is by second fundamental theorem of calculus. Okay, but this then, which I have proved so far, is norm of r prime t dt. If I call this double star, the last line follows by double star. Now this is a concrete formula by which we can calculate length of certain curves. So as an example, let me start with the upper half portion of the circle. So let us say RT equals to a cos t, a sin t, where 0 lesser equals to t lesser equals to pi and a is something strictly bigger than 0. So in the picture it would look like, if this length is a, I am looking at this portion of the circle, and you know from your elementary mathematics knowledge that this is actually pi a. So we will try to see whether I get pi a. By my formula, then lambda 0 pi is integral 0 to pi square root of x prime t square plus y prime t square dt. for me xt is a cosine t and yt equals to a sine t, t lies between 0 and pi. I can put all these quantities to get lambda 0 pi, that is equals to integral 0 to pi square root of a square sine square t plus a square cos square t dt, that is a times integral 0 to pi dt, that is pi a. So it matches with what we know from elementary geometry, that length of the upper half of the circle is pi a. Then using symmetry you can certainly say that total length and the additivity, that the total length of the circumference of the circle would be 2 pi a if a is the radius. So this is the radius, which is a. Another example would be, suppose the curve is not given in the parametric form, so just f is given from AB to R. Then I can look at the curve RT equals to TFT. That also represents the function as a curve. If I want to know the length of this, then what is lambda AB? This is integral a to b square root of x prime t square plus y prime t square dt, which is integral a to b. Because xt is t, that means x prime t is 1, so it is 1 plus yt is ft, so y prime t is f prime t square dt. So when the curve is given in the form as a graph, then the length of the curve turns out to be integral a to b square root of 1 plus f prime t whole square dt. Now we give you an example of a non-rectifiable curve. The curve is written here, ft equals to t cos pi by 2t if t lies between 0 and 1 and 0 otherwise. To show that it is not rectifiable, what I do is I choose a collection of partitions. One such partition is written here. For each n, I can define Pn to be this. I will try to show that mod pi Pn, that goes to infinity as n goes to infinity. That means all the pi p's, as the p's varies over partitions, are not bounded above by some number, and hence the curve is not rectifiable. To check this, what I do is mod pi Pn is anyway summation k from 1 to n norm of RTK minus RTK minus 1. If I write it in this form, all I have to do is I have to look at quantities like 1 by k minus 1 by k plus 1 whole square plus 1 by k cosine k pi by 2 minus 1 by k plus 1 cosine k plus 1 pi by 2 square whole to the power half, and then sum over k's for one partition P. Okay, k will vary from 1 to n or some such thing. Now, looking at cosine, I know that cos pi by k pi by 2 equal to 0 if k is odd, and if k is even, it's plus minus 1 if k is even. So whether k is even or odd, one quantity here or here would be 0. If k is even, then cos k plus 1 pi by 2 is 0. If k is odd, then cos k pi by 2 is 0. Using that, I can say that the above quantity is bigger than or equals to 1 by k or 1 by k plus 1. In any case, it is bigger than or equals to 1 by k plus 1. And hence, this would imply that mod pi p, since I am summing over the k's, is bigger than or equals to half plus 1/3 plus so on up to 1/nth. But I know that the right hand side is the nth, almost the nth partial sum except the first term, is the nth partial sum of the divergent infinite series 1 by n. So it goes to infinity as n goes to infinity. This implies the curve is not rectifiable. Well, this is happening because if I look at the differentiation or the derivative of the function ft minus f0 by t, limit t going to 0, this is limit t going to 0, t cos pi by 2t into 1 by t, that is limit t going to 0, cosine pi by 2t. But this limit does not exist. So it's not a differentiable curve, and as a result, I could see that it is not rectifiable. Well, it's not really if and only if, but since it is not rectifiable, there must be something wrong with the derivatives. That's what I wanted to check. It turns out to be the case. So there do exist curves which don't possess length. They are some weird curves. But rectifiable curves are those for which the length exists. And if the curve is rectifiable, in that case, I could show you that using the theory of Riemann integration, it is possible to find the length of the curve using some integral expression, which is neat, and given the data, one can use it to calculate the length of the curve.